Hey kids, time for some more math with definite integrals. And this time we are going to talk about average value. Now I want you to reflect back on elementary school math and learning how to take an average, right? This is average value of a function. Don't confuse that with the average rate of change. When we were doing derivatives, we talked about the average rate of change, and that was the slope of a secant between 2 points, right? So for instance, you might have had a graph, you might have had some function that looked like that. And I said between A and B, the average rate of change was the slope of that secant, right? And then we talked about the mean value theorem for derivatives, saying as long as you were continuous on that closed interval and you were differentiable on the open interval, then you were guaranteed at least one tangent line that was parallel to that secant, and the x values where that would occur were going to be between A and B, right? That was for derivatives. We are doing antiderivatives or definite integrals, and we are taking the average value of a function over that interval. So look at this crazy graph of the worth of Bitcoin, right? Starting when in February and ending of 1 year and ending, right, 2017 to where 2018 started. Crazy, crazy, right? So the Bitcoin's value started low and kind of steadily was the same for a while, but then there was some variations, but then a crazy spike. What's the average number, the average value, right, over this time interval? Start, stop. I wonder what the average Bitcoin price was. Now notice that function is continuous. It's not differentiable because look at all those sharp corners, but I can integrate it. Right? Now notice that the domain values are months, and the y values are dollars, right? And when you want an average value, you just want dollars, right? If you were to integrate this Bitcoin function, you would be integrating Bitcoin function times those domain values starting in February of 2018 and stopping, maybe it's in February or January, I don't know, of 2018. Your function, what would the units on your answer be? The units on the answer. Well, these are, right, this is money and this is months. So when you integrated, which means, right, I'm drawing rectangles under here and adding up the areas of the rectangles, what meaning would that have, right? Drawing all these rectangles, 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 right? Adding all of them up. What would the unit, I'd get some number, but what would the units be? Month dollars? Dollar months? I don't know how useful that is. What does that even mean? Huh? Well, I'll tell you what it doesn't mean. It's not the average value. The average value of the Bitcoin prices is a Bitcoin price. It's not a price month, a month price. So what the heck, right? Whatever this number and value is, it's in dollar months. That's meaningless to me. I wonder what I can do. So first, let's generalize the notion of average, right? And again, what I'm trying to figure out is how do I relate what we're doing with definite integrals to finding the average value of the function over time? Well, let's go back to elementary school again. What's the average of the following 5 temperatures? No big deal. Add those 5 numbers and divide by what? 5. But look how fancy I can make that. The average temperature is the sum of all the individual temperatures divided by how many numbers you have, starting with your first temperature value and stopping with your 5th temperature value. Right? So fancy. But instead of 5 discrete temperatures, what if I wanted the average temperature over 24 continuous hours? If I give you a temperature function. So there is a terrible interpretation of a function over 24 hours. So on the y-axis is my temperature in degrees Fahrenheit, and I'm saying that at time 0, so let's say that's daybreak, right? At the beginning of the day, so 12 a.m., I'm at 0 degrees. And that very symmetrically, as time goes through the day, right? Time is continuous. As time goes for the 24 hours, the temperature rises to a max and then falls. Now, that's not really how, but you can kind of see, right? It's colder colder at midnight. Temperature gets warmer and warmer. Temperature goes up, and temperature comes back down by, 12 a.m. the next day. Well, if I draw rectangles under that curve and add up the areas of those rectangles, and I do that to infinity, as the number of rectangles goes to infinity, I fill in all of these areas and I shrink those down to the curve, and I get the exact area under the curve. But again, talk to me if I'm integrating heights, what units are my heights in? Degree Fahrenheit. What units are my dx's in? All these dx values are hours. So I'm going to get some number out of that, and the units are degree hours? Huh? I don't get it. Well, again, let me say, if I'm dividing this up into rectangles, remember we talked about a uniform width of the rectangle, right? Uniform delta x is going to be b minus a, which for me would be 24 minus 0 over however many rectangles I had. Oops, sorry. But I want you to solve that equation for n. So in other words, this is 24 minus 0 over n. Solve that equation for n. Isn't that just 24 over delta x? And you're thinking to yourself, why would she do that? Well, bear with me. Stay with me. Stay on target. The average temperature is approximately the sum of all the individual function heights divided by n, right? All the individual temperature values that I get from my function, instead of just getting 5 discrete values, divided by how many temperature values I have. Well, look at what I replaced n with. You see what I did there? N is the same as 24 over delta x. So I put 24 over delta x in that denominator. Though I don't really like fractions within fractions. So look what I did with myself. I'm so smart. All these function values divided by 24 over delta x is the same thing as all these function values times delta x over 24. Right? Multiplication is commutative. I took this delta x and I put it at the end. And I left 1 over 24 in the front. And then I wrote the sum of all those function values as the sum of all those function values times delta x. But notice what I have here. Hello, George. That's George Riemann. How do I get the exact temperature? Don't you take a limit? An infinite Riemann sum, but in comes, come on, Leibniz. Come on, in comes Leibniz. So here's George. I took that 1 over 24. Here's George, an infinite Riemann sum. And I made him more elegant. Leibnizized him. And then I have this, where did this 1 over 24 come from? Oh, right. The interval. So wait a second. What was I doing again? Average temperature. The average temperature of a continuous function over a closed interval is an integral divided by its interval. The average temperature is exactly the integral over the interval. Whoa. Now think about the units. Remember we had those weird units? We understand that the function units are in degrees. The dx units are in hours. So the numerator is degrees times hours, but look at the denominator. You're dividing by this interval. Where is that interval? The interval is on the x-axis. Those units are hours. So you're dividing degrees times hours by hours. What do you get? And didn't we want the average temperature? We didn't want the average temperature times hours. We just wanted the average temperature in degrees. Oh my Lanta. That's a y value. What just happened? That's insanity. The average value of a function is the integral over the interval. So let's do this. Let's pretend I had a different function. Let's suppose I had the function y equals x from 0 to 10. What is the value? No units. What is the value of that integral? Remember I taught you that in the last video? This is just a triangle. dx is positive. This point is 10 comma 10. So the area is 1/2 base times height. That integral is 50. What's the average value of the function from 0 to 10? It is the integral divided by the interval five is on the y-axis. Look at that purple rectangle. The area of that purple rectangle is equal to the area under the area of that triangle, because look, this area that's above the purple rectangle fits down into here. Isn't that crazy? Going back to our temperature. No, let's not go back to the temperature. Let me stay with that function up there. The average value was equal to 5. Right? The average value of the function x from 0 to 10 is the integral, which was 50, divided by the interval, which is 10, and I got 5. 5 units. 5 right? Cool. So the average value of a function, if the function is integrable, and remember, all you need to be able to integrate is continuity. If you are continuous on a closed interval, then the average value of the function, which means a y value, a domain value, on that closed interval, the average value of the function is 1 over the interval times the integral, which of course is the same thing as the integral divided by the interval. Now I want you to look at this equation, right? Average value, integral over interval. So let's do this example first, and then I want to do some manipulation with this equation. Now, find the average value means you say, I'm going to integrate 0 to 3 of the function heights times dx, the integral over the interval is my average value. Now, this would be given to you right now on a calculator portion because you don't know how to integrate this. You would Math 9 that. So you would go to Math 9 from 0 to 3 of the function 1/2 x squared with respect to x, and you would get 4.5. That's the value of the integral, and you would divide that by 3, and you would get 1.5. AP is going to test you on this by formula, which is what you just did, and graphically. And I'll show you what I mean by that. So by formula, I just did, boom, integral over the interval. It was on a calculator portion. So even when I know how to integrate, I still would math 9 that and divide by 3. Remember, 1.5 is a y value because when you're doing the integral, you are multiplying function heights, which are y values, times domain values, which are x, and then you are dividing by the interval, which are x values. The x's cancel out, and you get a y number. Here's what I mean by graphical. How AP wants you to talk about this graphically. I want you to look at this equation. And remember, you can do whatever you want to one side of an equation as long as you do the same thing to the other. I want you to multiply both sides of this equation by b minus a. So I want you to multiply this side of the equation by b minus a and this side of the equation by b minus a. B by, what now does this, what statement do I have? The integral is equal to the interval times the average value. What? What? Wait a second. Wait, let me think about this. This is deep. The area under, as long as f of x is positive, the area under the curve is the same thing as width times height. Width times a constant height. Width times a constant height. What is that? The area of a rectangle whose height is, what's the height? Whose height is the y average. What the heck? Here's how AP is going to ask you to graphically show what the y average is. There's f of x, right? My heights come from 1/2 x squared going from 0 to 3. The integral is that area. That's 4.5. Y value, right? And this is 3 comma what? 3 squared is 9 over 2. Where's 3/2? If that's 9/2, 3/2 is about here, right? Starting at 0 and stopping at 3, draw a constant height of 3/2. Look at that rectangle. the area of the rectangle whose width is b minus a and whose height is the y average. The area of that purple rectangle is equal to the area of a rectangle with a width of b minus a and a height of the y average is equal to the area under the curve. The blue area is the same as the purple rectangle because all of this blue area that's on top of the rectangle will smoosh down and fit exactly into here. If you've done your y average right. Oh my Lanta. That's what they want you to do. When AP tests you graphically on average value, they want you to talk about the rectangle whose height is the y average bar and how the area under the curve will all fit into that average value box. It will fill it up. As long as your width is b minus a, in this case 3 minus 0, and the height is the y average value, 3/2. What? Math is cool. Forgot I did a better. I did a nicer animation of this and I just forgot that I had it in there. Whoops, sorry. Right, so there is a better representation of, this is 9/2, right? This is 3/2. The rectangle with the width of b minus a and a height of y average, the area of this yellow rectangle is exactly the same as the area under the curve. AP could ask you to estimate the y average by drawing this height. So you have to eyeball where to draw that height. Okay? Don't draw it too high, don't draw it too low. Draw the y average. Now, I was able to compute this, but what if I had just said, I didn't tell you what that was. I just said y was equal to f of x on 0 to 3. Could you draw me an estimate of y average? They want you to draw a horizontal line starting at 0, stopping at 3, and say all the area that is above the purple line would smush down and fit into the area here that is above the curve but below the purple line. Crazy. Mean value theorem. And we're back. The mean value theorem for definite, not for derivatives, for definite integrals. As long as you are continuous, remember the mean value theorem for derivatives need you to be continuous and differentiable. If f is just continuous on a closed interval, then at some point at c, f of c is equal to the average value. Right? So we say for a continuous function at some point on the interval, the actual value will be equal to the average value. Crazy. All right, we will talk more about this in our live session. This picture again shows the idea of an unknown function. F of x is in red. It is continuous on a closed interval. If I had to estimate, right, the average value, I would draw a horizontal line that starts at A and stops at B. It would be horizontal, and my guess would be drawing that line such that all the area above the rectangle but below the curve would fill in this piece that is above the curve but under the rectangle bar. This C value, right, f of C, C is in between A and B. Okay, cool?